Section 1. Competitive Analysis. Factors governing mechanistic pathways. Predicting the major product of a reaction requires a systematic analysis of the competition between SN1, SN2, E1, and E2 pathways. The primary variables determining the outcome are substrate structure, reagent properties, solvent effects, temperature, leaving group ability, and reagent concentration. The degree of substitution at the electrophilic carbon strongly influences both the stability of possible intermediates and the steric accessibility of the reaction center. For methyl and primary substrates, strongly favor the SN2 pathway due to minimal steric hindrance. However, SN1 and E1 pathways are generally inaccessible in these cases because primary carbocations are energetically unstable, unless resonance stabilization is present, such as in allylic or benzylic systems. In the case of tertiary substrates, direct nucleophilic attack is severely hindered by steric bulk, which effectively prevents the SN2 pathway. Under strongly basic conditions, E2 elimination predominates. Meanwhile, in the presence of weak nucleophiles or weak bases under solvolysis conditions, the reaction proceeds through carbocation-mediated SN1 and E1 pathways. Secondary substrates represent the most competitive scenario of all. In these systems, the dominant pathway is highly sensitive to the specific nature of the reagent and the surrounding solvent environment. The second factor involves reagent properties, specifically the balance between nucleophilicity and basicity. Strong nucleophiles and strong bases, such as hydroxide or alkoxide ions, typically promote bimolecular pathways. These lead to either SN2 substitution or E2 elimination depending on the specific steric conditions of the substrate. When bulky bases such as potassium, tertiary betoxide, or LDA are used, steric hindrance reduces their nucleophilicity, making proton abstraction more favorable. As a result, E2 elimination is promoted, even in substrates where SN2 would normally dominate. Finally, weak nucleophiles and weak bases, such as water or alcohols, favor unimolecular pathways. They do so because they are not sufficiently reactive to directly displace a leaving group or remove a proton prior to the ionization of the substrate. The choice of solvent also plays a critical role in directing the reaction pathway. Polar Aprotic solvents, such as DMSO, DMF, or acetone, enhance the reactivity of anionic reagents by minimizing their solvation. This greatly increases nucleophilicity and promotes bimolecular pathways, such as SN2 and E2 reactions. On the other hand, polar Protic solvents like water or alcohols stabilize the carbocation through solvation by lone pairs and the leaving group through hydrogen bonding. This stabilization lowers the activation energy for the rate-determining ionization step, which favors SN1 and E1 reactions. Temperature is another decisive factor because elimination reactions typically generate a greater number of product molecules than the reactants, resulting in a positive standard entropy change. According to the Gibbs free energy equation, where delta G equals delta H minus T delta S, increasing the temperature increases the magnitude of the negative T delta S term. As a result, higher temperatures thermodynamically favor elimination pathways like E1 and E2 relative to substitution reactions such as SN1 and SN2. The fifth factor to consider is the leaving group, which acts as the starting signal for the entire reaction. Its nature not only affects the reaction rate, but can also influence which mechanistic pathways are accessible. Leaving group ability generally correlates inversely with basicity. Weaker bases, the conjugate bases of strong acids, make for better leaving groups because they can more effectively stabilize a negative charge after they depart. This factor plays a particularly important role in reactions that involve carbocation formation. Excellent leaving groups, such as iodide or tosylates, readily depart on their own. This facilitates carbocation formation and therefore promotes SN1 and E1 pathways. In contrast, poor leaving groups, such as fluoride or hydroxide, are much less likely to ionize spontaneously. In these cases, the reaction usually requires a strong nucleophile or base to drive the reaction through SN2 or E2 mechanisms. Finally, bimolecular and unimolecular mechanisms respond very differently to changes in reagent concentration. For bimolecular reactions such as SN2 and E2, the rate depends on both the substrate and the reagent concentrations. Since the nucleophile or base is directly involved in the rate-determining step, increasing the reagent concentration increases the reaction rate. In contrast, unimolecular reactions like SN1 and E1 depend only on the substrate concentration. In these cases, the rate-determining step is the ionization of the substrate to form a carbocation ion, a step that does not involve the nucleophile or base. As a result, raising the concentration of a strong nucleophile or base strongly favors bimolecular pathways, while unimolecular mechanisms are hardly affected. In short, the higher the reagent concentration, the more likely it is that a bimolecular mechanism will dominate. Section 2. Mechanistic Considerations. Refinement of product identity. Once the most probable mechanism has been identified, additional factors must be evaluated to determine the precise regiochemical and stereochemical outcome. In mechanisms such as SN1 and E1, whenever a carbocation ion intermediate forms, one must consider the possibility of rearrangement through 1,2 hydride shifts, or 1,2 alkyl shifts. These rearrangements occur when they lead to a more substituted and therefore more stable carbocation ion. The stereochemical outcome depends heavily on the specific pathway involved. For instance, SN2 reactions proceed through a concerted backside attack, resulting in a complete inversion of configuration at the stereocenter, a process known as Walden inversion. In contrast, E2 requires an anti-periplanar arrangement between the beta hydrogen and the leaving group. In the Newman projection, this corresponds to a dihedral angle of approximately 180 degrees. This geometry allows optimal orbital overlap, enabling efficient formation of the pi bond in the transition state. For SN1 reactions, the formation of a planar carbocation ion intermediate theoretically results in racemization. However, partial inversion is often observed in practice due to the ion pair effect, in which the departing leaving group temporarily shields one face of the carbocation ion from the incoming nucleophile. In E2 reactions, regioselectivity is governed by two competing rules. Zaitsev's rule predicts the formation of the more substituted, and therefore more thermodynamically stable, alkene as the major product. On the other hand, Hofmann's rule predicts the formation of the less substituted alkene. This outcome typically arises when bulky bases are used, or when significant steric effects destabilize the transition state that would otherwise lead to the Zaitsev product. To wrap up, we have summarized the key points of each reaction in a single table. We hope this helps you consolidate your understanding. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.